Before we go on with our next topic, I need to go back to the problem that we started with, that we finished in the previous video. So it's asking us to let's go back and rewrite the algebraic form of the Ka expression. So if you remember in the previous video, the equation was dealing with acetic acid plus water was in equilibrium with acetate ion, CH3COO minus, plus H3O plus. And we said that the Ka expression was the concentration of acetate ion, COO minus, times the concentration of H3O plus divided by the concentration of acetic acid. Okay. All right. Now, if we pop in our values that we had for those concentrations at equilibrium previously, the value was for the acetate ion was 0.05 minus X times the concentration of H3O plus, which was plus X, divided by the concentration of acetic acid, which was 0.05 minus X. Okay, and this was all equal to Ka. All right, now, because we could safely assume that X was small, what was the result? So for that first question, we said that because X was small, what was the result? The concentrations cancel out. So X could be any value. Now, it turned out that the value that X was the Ka. All right. Now, here's our next part. Let's say the initial concentration of the conjugate acid, so the acetic acid, was twice that of the conjugate base instead of equal. Write the mathematical expression. So here's our Ka. Ka for the original reaction. So I'm saying that it was the concentration of the acetate ion times the concentration of hydronium ion divided by the concentration of acetic acid. So what I'm trying to say in this problem is, what if we did this problem and instead of having equal amounts of the weak acid and its conjugate base, what if you had double the amount of the acid? So twice the amount of the acetic acid. Okay. So they would still cancel out, but look, our expression now is the concentration of H3O plus over 2. And so if we solve for the concentration of H3O plus, as we want to do for these problems, it's really going to be twice whatever the Ka value comes out to be. Okay, so if X is still small enough to ignore, what do you get? That the concentration would be equal to twice the Ka. So we can also derive a pretty useful equation to help us out for this. So let's write the Ka general chemical equation where you have an acid plus water is in equilibrium with a conjugate base plus H3O plus. Okay. And so we're going to write this Ka expression in terms of concentration. So the Ka would be equal to the concentration of the base times the concentration of H3O plus divided by the concentration of the weak acid. And this is old hat now. You guys are used to writing these Ka expressions. All right, now, because we often need to find pH, let's rearrange this equation for the concentration of H3O plus. So I want to get H3O plus by itself. All right, so what I'm going to do is multiply both sides by the concentration of the acid. So Ka times the concentration of our weak acid is equal to the concentration of the base times the concentration of H3O plus. And so if we divide both sides by the concentration of the base, the concentration of H3O plus is equal to Ka times the concentration of the acid divided by the concentration of the base. Okay. Or if I want to get real, let's get a little clear with this. Let's say I just want to have a ratio of the acid to the base. I could also rewrite it this way, that Ka times the concentration of the acid divided by the concentration of the base. Okay. Now, what I'm going to do is take the log of both sides. All right, so if I need to take the negative log, sorry. So I'm going to take the negative log of H3O plus, all right, and that's equal to the negative log of Ka. And then because we're multiplying these two, I'm going to take the negative log of the acid over the base. Okay, so there's a reason why we did this, because look, the negative log of the concentration of the H2O plus, that by definition is pH. Negative log of Ka, that by definition is the pKa, and then you'll have minus log of the acid, concentration of the acid, over the concentration of the base. And so this equation that we have, this equation right over here, this is a really famous equation that we call the Henderson-Hasselbalch equation. So if you're really good at predicting when X is going to be small, not with the initial acid or the base or not near equivalence, you can actually use the Henderson-Hasselbalch equation to solve the pH of titrations as well as mixtures of a weak acid or a weak base pair. So that's pretty cool. Now, either in a titration when comparable amounts of acid and base are present, or when making a mixture of the pair, the solution is called a buffer. And a buffer, another way to think of a buffer is something called a chemical sponge. And I'm going to explain why that is in a minute. Because what a buffer does is resists change to a pH. Resists changes to pH, sorry. Okay. And that means that excess H3O plus reacts with your weak base, and excess OH minus reacts with the weak acid. Okay, and we can do calculations in reverse. If you have a desired pH, but you need to calculate how much acid and base you need to get the desired buffer. All right, so let's try this out. What must be the ratio of acid to base to acid if you want a buffer with pH 4? Okay, so again, here's our equation. Let me be clear a little bit about this. All right, so the pH is equal to the pKa. Now, the way this was written, we have the log of the concentration of acid over the base. If we switch it around, where we get the base over the concentration of the acid, all we have to do is subtract that minus, move that minus sign and change it to a plus sign. So there you go. Okay. All right. Now, in the previous problem that we were dealing with, the Ka of acetic acid was 1.8 times 10 to the minus fifth. And since we calculated in the last problem, the pH was equal to the pKa, which was 4.74. So those are values, yeah, that we were dealing with earlier. All right, so I want to know what's the ratio of base to the acid that I need if the pH of the buffer is going to be at 4. All right, so what I'm going to do, let's pop in our numbers. The pH has to be equal to 4. The pKa was 4.74 plus the log of base over acid. Okay, so if I subtract 4.74 from both sides, I get that the log of the base over the acid, that's going to be equal to negative 0.74. Now, I can undo that logarithm by raising everything to the power, that's going to be my exponent to the base 10. Okay, so if I do that, if I make everything that I had written previously my exponent to the base 10, I get that the concentration of base over the concentration of acid is going to be equal to 10 raised to the negative 0.74 or 0.18. So what this means is that if I have a 1 molar concentration of acid, I need 0.18 moles of base in order to make a pH of 4, based on what I've got. Now, here's the next thing. Let's say the concentration of acid is 0.1 molar, as above. What's the concentration of base? All right. So here's what we got. The concentration of base over the concentration of the acid is equal to 0.18. Okay. So what I'm going to do, if we need to get the base by itself, the concentration of base, if I multiply both sides by the concentration of acid, 0.18 times the concentration of the acid. Now, if I know that concentration of the acid is 0.1 molar, and put that in, 0.18 times 0.1 molar, okay, the concentration of base should come out to be 0.018 molar as well. So that's kind of nice. If you know one, you can figure out the other one. Let's take a look at this problem. Compare the effect of adding a strong base to a strong acid versus a strong base to a buffer, starting at pH 4 in both cases. All right, so here's our first problem. How much HCl do you need to add to 1 liter of water to get a solution with pH 4? All right, so here's how we're going to do this. We know that the pH that we're shooting for is 4, okay? And if you remember, the way that we deal with a strong acid is that, let's say HCl plus water is going to form an equilibrium, but we know it's going to go all the way to completion with H3O plus and Cl minus. Okay, and that's H3O plus is what we're looking for. All right, so we know pH by definition is equal to the negative log of the concentration of H3O plus. And to solve, if we were solving for the concentration of H3O plus, the concentration of H3O plus would be equal to 10 raised to the minus pH. Or 10 raised to the negative 4, which would be 0.0001 molar. All right. So how much HCl do you need to add to 1 liter of water? Well, if this is your concentration, okay, and remember molarity is 1 mole per liter. If we multiply this by 1 liter, we're going to add 0.0001 moles of HCl. All right, so that's how much acid we need to add. Second, what will be the pH? What will the pH be for the solution if you add 0.0010 moles of sodium hydroxide? Okay, now since you're dealing with HCl, a strong acid, and NaOH, a strong base, our equation that we're dealing with is the autoionization of water. 2H2O yield is in equilibrium with hydronium ion plus hydroxide ion. Okay, so initially, you know that you've got the concentration of hydronium ion, which was 0.0001 moles, and the hydroxide is 0.0010 moles, and you've got no water. Completion moles, you know you're going to run out completely of the H3O plus. And for the hydroxide, if you subtract out the acid that's being used up, you're going to end up having 0.00, let me erase that negative sign, 0.0009 moles. Okay, and so if we get the molarity here, completion molarity, and assume that we have 1 liter, okay, the completion molarity would be 0 molar for H3O plus, and you'd have 0.0009 molar for hydroxide. So that way, at equilibrium, the molarity would be plus X for H3O plus, and 0.0009 plus X for the hydroxide ion. If we solve for Kw, Kw is equal to the concentration of H3O plus times the concentration of OH minus. So that would be X for the concentration of H3O plus, 0.0009 plus X for hydroxide ion, and that's equal to 1.0 times 10 to the minus 14th. Now, if we assume that with the approximation that X is not going to change all that much, okay, then that concentration for the hydroxide is really just 0.0009. So that would be 0.0009x is equal to 1.0 times 10 to the minus 14th. X, if we divide both sides by 0.0009, X should give you 1.11 times 10 to the minus 11th. All right, so that's going to be your pH of the H3O plus. We can solve for pH. That's the concentration of H3O plus. We can solve for pH because that's the negative log of the hydronium ion, and that pH comes out to be 10.95. All right. Now here's our third part. What would be the pH if we add 0.0010 moles of sodium hydroxide to 1 liter of the buffer we've described here? All right, so you're adding more base to this buffer that we just had. All right, so you have two different reactions going on. You've got a Ka reaction that's saying this, that acetic acid plus water is in equilibrium with acetate ion plus H3O plus. And you got a Kb expression that says that the acetate ion plus water is in equilibrium with acetic acid plus hydroxide ion. All right, so because we're adding this much of the base, we need the Kb expression. We need the Kb equation for this. So let's use that equation. For the acetate ion, according to the previous problem over here, the acetate ion was 0.018 molar. And assuming we have 1 liter, that would be 0.018 moles. Okay. For the acid, that was going to be 0.100 moles. And we're adding, for the hydroxide, 0.0010 moles of that. All right. So which one's going to run out first? Well, we're going to run out of hydroxide ion first before anything. So the completion moles, we're going to have no hydroxide left. But if we subtract out the 0.001 from the acetic acid, that would give you 0.099 moles of acetic acid. And because we're adding, we would be adding on the other side 0.019 moles of acetate ion. All right, so if we have the completion molarity and everything's 1 liter here, that means the molarity of the acetate ion would be 0.019 molar. The concentration of the acetic acid would be 0.099 molar. And then the concentration of the hydroxide ion would be 0. So that way, at equilibrium, concentration of acetate ion would be 0.019 minus X. Concentration of acetic acid would be 0.099 plus X. And the concentration of hydroxide ion would also be plus X. All right. So we need to get a Kb value for this. Remember that Ka times Kb is equal to Kw. So Kb would be equal to Kw divided by Ka, or 1.0 times 10 to the minus 14th divided by the Ka value, which was 1.8 times 10 to the minus 5th. And so that comes out to be 5.56 times 10 to the minus 10th. So we have our Kb value. If we pop in, now that we have Kb, and write our Kb expression, that's going to be the concentration of acetic acid times the concentration of hydroxide ion divided by the concentration of the acetate ion. Okay. All right, and that's all equal to 5.56 times 10 to the minus 10th. If I put those concentrations in that we've got in the equilibrium, acetic acid was 0.099 plus X, hydroxide ion is X, and then acetate ion is 0.019 minus X. That's going to be equal to 5.56 times 10 raised to the minus 10th. Okay, so if we apply the approximation, so if I and then rewrite things, so the x's will cancel. The x, because the x's are going to be small, they're going to inside those expressions. They're not gonna matter. So we're going to have something like this: 0.099 divided by 0.019 times x is equal to 5.56 times 10 to the minus 10th. Okay, so if I solve for x, all right, let's take 0.099 divided by 0.019. That's going to give us about 5.211x is equal to 5.56 times 10 to the minus 10th. And if we divide both sides by 5.211, that's going to give us a value of 1.07 times 10 to the minus 10th. Okay, and so that's going to be our concentration of hydroxide ion. All right, so now using that, we could find POH because that's going to be the negative log of hydroxide ion. The POH would come out to be 9.97. And then to find the pH, if we take 14 and subtract the POH from this, the pH comes out to be 4.03. And so there it is. All right. Okay, so here's our next problem. Do this last calculation using the Henderson-Hasselbalch equation rather than the 4-line method. It tells us to be careful. So here's what we're going to do. So the Henderson-Hasselbalch equation says this, that the pH is equal to the pKa plus the log of the concentration of base over the concentration of the acid. All right. Now, the pH is what we're solving for. The pKa is 4.74. Now, the concentration of base over the concentration of the acid. Base is going to be your acetate. Acid is your acetic acid. Let's go back up here. So initially, we had 0.018 moles of the acetate ion and 0.1 moles of acid. And we're adding 0.001 moles to the base, and we're taking it away from the acid. So we end up with these values. All right, so let me write this out. So let's start with log. Now, what I'm going to do is write the base. The base is going to be the initial, which for us was 0.018 molar, but we're adding 0.001 moles to that. Okay. For the acid, we had 0.100, and we're subtracting 0.001 moles from that. So that really becomes 4.74 plus the log. For the base, that would be 0.019 molar divided by 0.099 molar for the acid. And if you solve, that comes out to be 4.02. So even though we pretty much got the same value that we got doing it the longhand. But that's it. That's how a buffer works, and that's how the Henderson-Hasselbalch equation also works for a buffer.